Welcome everybody back to our course on memory device technology for AI/ML computing. So in the last class, we concluded our discussion on bio-inspired spiking neural networks. And today will be the beginning of our concluding topic on in-memory computing. But before that, let's do a brief recap of what we studied the last time around. So basically, first, we looked at how threshold balancing can be used at every layer of a trained deep neural network to completely convert it into a fully converted and fully scaled spiking neural network, and that too without compromising the accuracy. Now, this appears to be one of the most practical approaches to building large scale spiking neural networks, at least for inference only systems. Next, we went ahead and examined several hardware implementation of spiking neural networks, starting from IBM's True North, the Spinnaker project of the ARM microprocessor, and also Intel's Loihi architecture. The common theme across all these architectures was that they use a digital event-driven implementations, especially in the GALS architecture. Remember what was GALS? Globally asynchronous, locally synchronous network of spiking neurons and synapses. They rely on asynchronous routers, packet-based spiking communication, and programmable neuron models rather than attempting a full-scale analog emulation of all the biological dynamics. And this digital approach is what makes these systems very scalable and robust, although it limits the bioplausibility. Also, we discussed some key challenges preventing a full-scale analog implementation of large-scale SNNs for really complex tasks. They were primarily device mismatch and noise, which had limited precision, and therefore you had the difficulty of making these adaptive learning rules purely analog and implementing spiking neural networks only for simple pattern recognition or low dimensional sensory tasks. So this naturally led us to the idea of using mixed signal spiking neural network implementations, such as that we saw in Brainscale and also in NeuroGrid chips. So these platforms use the analog neuron and synapse dynamics for energy efficient computation, but surround them with digital control and communication networks for better scalability. And this hybrid approach or the mixed signal approach combines the best of both worlds, the analog efficiency and the digital stability and scalability. So in today's class, we shift our attention to the final topic, which is how do we further improve the computational efficiency in AI/ML systems using a concept called in-memory computing. And as we will see, one of the main advantages of in-memory computing is that we don't necessarily need to make drastic changes or exotic alterations to our current memory or compute elements. So let us begin with understanding what is the need or the philosophy behind in-memory computing. And this is a great moment because it brings our course back to a complete full circle. Remember where we began our first lecture with. On day one, we started with the von Neumann architecture. So I hope you are now very familiar with the von Neumann architecture and the separate logic and memory elements and this data bus that connects this logic and memory elements. And right at the beginning, we saw that even for doing very basic computational tasks like fetching two numbers, A and B, from the separate memory locations, bringing them to the logic element, adding them up at the arithmetic logic unit, and then pushing the data back into the memory element is a rather sequential task. And most of the time in the sequential task was actually spent in data movement. So the time that was required or the latency that was incurred in von Neumann systems is primarily due to data movement, and it takes very little time actually for you to do the ALU operation. And we went into a lot of detail into why that is the case. We saw different kinds of memory walls at the interface of your processor subsystem and the main memory, and also between the main memory and the IO bottleneck between the main storage. However, one of the key lessons from our course is that when we move towards data-driven computing regime, which is your AI/ML computing tasks, this data movement results in not just very large amount of latency, but also huge amount of power consumption. And we figure out that most of the power consumption that happens in running these AI/ML tasks on one diamond architecture is from shifting data back and forth from the DRAM and also from the main storage. So an actual MAC operation or multiply and accumulate operation at the arithmetic logic unit, if it costs 1x the energy, the data movement to and fro from DRAM and NAND flash cost roughly 200 to 500 times. And this is what led to this unsustainably large power consumption in modern day AI/ML systems. And therefore, the key idea that we were trying to look at is how do we reduce this power consumption by minimizing the data movement in all these tasks, especially in the data-driven computational regime. And we saw in detail that the first approach is try to mimic the brain. When we try to mimic the brain in terms of neuromorphic architectures that we have been looking in detail, we look at the hardware model for neurons and synapses, how they behave, how they are brought together in spiking neural networks, and really helps in reducing power consumption. But one thing that we saw is that to get into the neuromorphic regime, there is a substantial overload in redesigning not just the computational architectures, but also the systems and the devices. So your current day transistors and memory elements may not be sufficient to usher in the neuromorphic regime. So although the neuromorphic computing is promised to be really low power, there are several hurdles that we need to cross before we get there. And therefore, people started asking, how do we achieve the same task, which is minimizing the data movement without having so many changes or with very minimal changes to the existing computational infrastructure. So it is more like a solution for the near term. And the idea that people came up with is, instead of having co-located memory and logic, as is the case in neuromorphic systems, why can't we perform logic operations within memory elements or using memory elements? And that is the key idea of in-memory computing, which is also called IMC or also sometimes called compute in memory. So what are the key advantages of performing in-memory computing? Of course, there will be very limited or absolutely no data shuttling between the processing elements and the memory elements. Why? Because you are performing logic operations with existing memory elements. Of course, to load the data before you do the logic operation, there will be some data movement, but that will be quite limited. And this is supposed to give you latency and power gains and of course higher throughput. But as you can see, I have put some question marks regarding whether they really give us better latency and power gains. And that we will see is the real challenge. And we need to do a very intelligent design to actually realize the profits of having minimal data shuttling. So we will discuss that in detail. And this is where we will also look at some challenges of implementing in-memory computing. That is, how do you redesign the data flow and do mixed signal peripherals? And what are the factors that prevent the scalability of in-memory computing? So with this introduction, let's go and try to look at the first generation of doing in-memory computing. But the first generation of in-memory computing was not really doing computing exactly inside the memory arrays, but doing computation physically close to the memory arrays. So let's talk about this concept, which is much more immediately achievable, and that is of near memory computing, or sometimes also called processing in memory or PIM. In this approach, we don't necessarily move the compute inside the memory element. Instead, we bring small logic units physically closer to the memory. Either you bring it inside the memory package or in the same stack or in the same die. So as you see, in the conventional architecture, the logic unit that normally sits inside the CPU and GPU is now placed right inside or right beside the memory chip. Now, this does not completely eliminate data movement entirely, but it dramatically shortens the distance that data has to transact between the logic and memory elements. So the idea is very simple. This logic unit, which is sitting right near the memory on the same die as the memory, can perform some of the very important, frequently used logic operations that are necessary for AI/ML computing, and the pre-processed data can now be sent to the main CPU or GPU unit. So near memory computing or processing is very practical and deployable with today's technology, and therefore forms the first generation on the path towards in-memory computing. And this has been very successfully demonstrated. So let us look at two examples from recent literature. The first example is of high bandwidth memory along with process in memory, which was demonstrated by Samsung's AquaBolt XL. So in this case, what you do is you have your high bandwidth memory. I hope you remember from the final portion of our DRAM, what was this high bandwidth memory? So this high bandwidth memory is normally stacked DRAM, which is placed very close to the CPU or the GPUs. In HBM PIM, these tiny processing core units called PCUs are integrated inside the memory stack right next to each of the DRAM banks. So in comparison to your earlier HBM, which had only DRAM banks, only memory storage, you are including a PCU unit which can do very simple operations that are frequently required, such as accumulations or reductions, without sending the data back and forth to the GPU. Now, the GPU still handles the main control and scheduling, but memory-intensive kernels like attention or embedded lookup tables can be now offloaded completely to the HBM stack itself. Now, this approach is what significantly reduces the movement of data while staying compatible with today's GPU ecosystems. And this dual advantages of HBM, remember the main advantage of HBM is the shortened path of signal transmission from two off-chip elements to putting the DRAM in the same die as your GPU and your process in memory PCU subsystems, which reduce the frequency of data transfer, really help in large gains in system performance in terms of latency and also energy reduction. Another example is the tensor DIMM shown here, which was also developed in South Korea. The idea here is slightly different. Here, instead of stacking compute with HBM, what we do is we add a small vector ALU and a lightweight memory controller inside the dual inline memory module. Remember what was your DIMM modules? It was these chips that you buy from Amazon and you plug it into your motherboard. Such multiple smart DIMMs together perform tensor operations. So they are together called the tensor node, which the GPU can access over a link, and therefore it will behave like an external memory pool, but now with compute ability. So what this tensor DIMM is particularly effective in is managing workloads such as doing large matrix multiplications, and therefore it drastically cuts the latency and memory bandwidth pressure. So with these two examples of process in memory, which is AquaBolt and tensor DIMM, we show how by bringing logic inside the memory chip, you will be able to offload some of the frequent memory transactions and logic processes inside the DRAM chip itself, and that too without requiring any radical changes inside the DRAM cell array. So with this, the natural question that arises is, can we push this idea even further? Instead of placing logic beside the memory, can we actually perform computation inside the memory array using different biasing conditions for bit lines, word lines, or even by modifying the device physics itself? And that is what brings us to our major topic, which is true in-memory computing, which can be implemented in two fundamentally different ways. That is your digital in-memory computing and your analog in-memory computing. So let us first start with digital in-memory computing. So as you can see, the structure of digital in-memory computing is such that you have the small PE or processing element nodes. So what does each processing element node do? It performs simple Boolean logic operations with your standard two-level SRAM and DRAM cells, just by modifying the peripheral circuitry and the biasing schemes. We will see examples very soon. The key advantage of doing digital in-memory computing is that you retain all the great things that is associated with digital computation. That is very high precision, very high compatibility with current GPU systems, and very high noise resilience as well. However, as you know, the density and power consumption in these systems will be much poorer as compared to analog in-memory computing. So what is analog in-memory computing? In analog in-memory computing, you do analog computation, especially matrix vector multiplication operations, and this can aid in direct acceleration of your artificial neural networks. Why is this the case? Remember that the key logic operation which consumes a lot of power and latency in artificial neural networks, which is happening at every node, whether it is in inference or in backpropagation, is your vector matrix multiplication. Now, if you can somehow make vector matrix multiplication one step using analog computation, you will solve the entire problem of having large power consumption in artificial neural networks. And this is generally achieved using multi-level electronic non-volatile memories. So here your simple two-level SRAM and DRAM conventional memory will not help. You will have to go to non-volatile memories, especially that which can offer you multiple non-volatile resistive states. But of course, you have to do a great deal of optimization in converting the digital data into analog form, where the computation can be done by the array, which consists of this ENVM crossbars, and then again converting this data, which is in analog form, back to digital for further processing. So as you can understand, you can have large improvements in density and power as compared to digital in-memory computing. However, you will be heavily limited by your precision and noise resilience capabilities. So in today's session, we will exclusively focus on digital in-memory computing, and in the next class, we will look at analog in-memory computing along with some hardware implementations of both digital and analog in-memory computing. So let's first see how conventional memory such as DRAM can be somehow tweaked only at the peripheral architecture and biasing scheme. You are not really changing the architecture of your DRAM cell. You are just biasing it in different ways to completely change the operation of the DRAM. Now remember, DRAM is normally just a bit storage technology, and somehow we are trying to change that so that we can do some logic operations in the DRAM memory itself. How is that done? Let's start with the example of performing OR operations in the DRAM cell. So before that, let us do a quick recap of how the read operation happens in the DRAM cell. Remember, the first thing that you do in your DRAM cell to find out whether the voltage stored in the storage node is 1 or 0 or VDD or 0 is first you pre-charge the bit line to VDD by 2, and then you assert the word line. When you turn on the word line, this particular access transistor turns on. Now, if the storage node had the value 1, which is VDD, and the bit line has VDD by 2, there will be a discharge or a read current flowing from the storage node into the bit line, and that will change your voltage of bit line from VDD by 2 to plus delta V dash. And the exact opposite will happen if your storage node consists of the value of 0. There will be a discharge in the bit line, and that is what will be detected by your sense amplifier. Now, the question we are trying to ask here is, if we have two cells, which is cell 1 and cell 2, consisting of storage node 1 and storage node 2, can we somehow change the biasing of word line and bit line such that the final output at the sense amplifier will give me the OR operation of VSN1 and VSN2? How do we achieve that? Common sense suggests that if we want to do a logic operation, instead of turning on the word lines one by one, you will have to simultaneously turn on the word line and somehow intelligently pre-charge the bit line such that the output corresponds to 0 when both VSN1 and VSN2 is 0, and for all other case, when either VSN1 or VSN2 are 1, the output of the sense amplifier should turn to 1. And if you think a little carefully about it, this can easily be achieved by first turning on the word line of 1 and 2 nodes together and also pre-charging the bit line to VDD by 4. How does that help? Let's look at these examples. So the two extreme examples are very simple. Suppose the bit line was earlier charged to VDD by 4 and your word line were simultaneously turned on in the case where both storage node 1 and storage node 2 had the value 0 stored in it. What will happen? Because this is VDD by 4 and this is 0, there will be a read current flowing from the bit line into the storage node from higher potential to lower potential, and this will definitely lead to the discharge of the bit line. And this discharge of the bit line can be easily detected from the sense amplifier to give an output of 0. So we have achieved 0 or 0 results in 0 using this biasing. The exact opposite is where both the storage nodes are 1, and as you can see from this diagram, this will result in the charging of the word line because both the storage nodes are at a higher potential as compared to the pre-charged VDD by 4 bit line. And therefore, you will also be able to achieve 1, which is the OR operation of 1 and 1 in storage node 1 and storage node 2. But what happens for these two intermediate cases? For these two intermediate cases, what essentially happens is that since this value is VDD by 4, that means that definitely there will be a read current which flows inside the storage node 0 and a read current which flows outside of the storage node of 1. But because the potential difference between VDD, which is at storage node 1, and VDD by 4 is 3 VDD by 4. Therefore, the value of the read current which will flow from storage node consisting of 1 into the bit line will be much more in magnitude compared to the one which is flowing inside the storage node 0, just by the virtue that the potential difference between VDD and VDD by 4 is greater. And therefore, there will be a net charging of the bit line which also will get detected as 1. So this is how, by doing very simple biasing schemes of bit line and word line, you are able to achieve the OR operation. Now think very carefully with the same way how you will be able to achieve the AND operation. So with this, let us look at how SRAM arrays can be used to perform logic operations, especially AND and NOR, directly inside the memory arrays. Now, we know that an SRAM cell just simply stores a bit across the two cross-coupled inverters, but in digital in-memory computing, we take advantage of the fact that when the word line is activated, the cell strongly drives the bit lines with its stored value. And this is the key trick, again, we use when we try to perform AND operations on the value which is stored in these two SRAM cells with nodes A and B. As you can see, first we load the operands into storage node A and B, and then we pre-charge both the bit line and bit line bar to VDD, just as it is done for the read operation. This is followed by asserting the word line for both the storage node 1 and the storage node 2, or storage node A and storage node B. Now please try to recall the way we designed the cell ratio of the SRAM cell. It is such that the read current which discharges the bit line wherever the value 0 is stored, but it is a non-destructive read because of the positive regenerative feedback. And this I read discharges the bit line, and therefore if both A and B were 0, it would be a very small value that you will detect over the V reference. The 0, 1 and 1, 0 combinations will be intermediate, and if both were 1 and 1, you would have no discharge at all in the voltage of the bit line. And this is how you are able to implement the AND operation for the storage nodes A and B. And similarly, you will be also able to see at bit line bar, you will just have nothing but the exact opposite or the complement of the AND operation. So this is how, by just playing with the biasing scheme of bit line bar and word line, and selecting the reference voltage to the sense amplifier smartly, you will be able to perform AND and NOR operations. Next, we show a very interesting concept where even analog multiply and accumulate operations can be performed with the SRAM cell. Now, this is not actually completely analog MAC operations, but multiplying an analog input with a digital matrix to get an analog output. What do I mean? Let me explain it through this particular circuitry. And the best way to understand that is to take a few values. So let us take the value of the input voltage to 0.5 volts and input 2 as 1 volt, and load or preload the SRAM cells with digital values of 1, 0, 1, 1, and see how this 1 cross 2 analog vector of Vin gets multiplied to this 2 cross 2 digital matrix of A11, A21, A12 and A22. And this is done by 3 steps as shown in this figure. In the first step, what you do is you turn on the first switch, and as you turn on the first switch at each and every node, what essentially happens is that the capacitor corresponding to each node gets charged to the value which is proportional to V in 1, and that is what I have written. V in 1 charges the capacitor to a value which is proportional to the input voltage. In the next step, we open the first switch and close the second switch. The moment we close the second switch, what happens is that the NMOS over here is connected to the Q dash of your SRAM cell. That means if this is 1, it is connected to 0. That simply means that if the value of the SRAM cell is 0, this capacitor discharges. For example, over in A221, this capacitor discharges because the NMOS here is turned on, and therefore only the values which have SRAM cell with 1 retain the charge after the second step. So here the charge before we have the third step is 0.5 multiplied by capacitor, which was the voltage multiplied by the capacitor. That's the charge on this capacitor. Here it is 0 because the value of the SRAM A21 matrix was 0. Here it is 1 C. Here it is 1 C as well. That is 1 volt multiplied by the capacitance of this capacitor. In the final stage, what you do is you open even the second switch and finally close the third switch. If you close the third switch, what will happen is there will be a charge sharing in all the capacitors. Now see, if there is a charge sharing between 0.5 C and 1 C, the net capacitance will be 0.75 into C, and here it will be 0.5 into C. The net V out 1 will be 1C plus 0.5 C divided by 2, and for V out will be 0.5 C plus 0 C divided by 2, and as you can see, the value will be proportional to the output. So actual output is 1.5. This is just half, or 0.5 into C, and similar is the case with V out 2 as well. So by using this very simple circuitry, you are able to multiply an analog vector input with a digital matrix. And this brings us to the next question. Normally in vector matrix multiplications, you need to multiply two analog numbers. How do you do that? And this is where analog in-memory computing will come into the picture, where we will see how we can transform a multi-level electronic non-volatile memory-based crossbar arrays to have analog vector matrix multiplication. This is what we will cover in the next class, and then conclude our course by looking at some of the implementations of in-memory computing. Thank you for your attention. See you in the next class.